This is Dr. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we are discussing the problems in radiations, which belongs to heat transfer subject. Here, the problem one is a furnace inside temperature of 2250 degree Kelvin has a glass circular viewing of 6 cm diameter. If the transmissibility of a glass is 0.08, make calculation for heat loss from the glass windows due to radiations. So first of all, identify the given data in the problem. Furnace temperature is given 2250 degree Kelvin. The diameter of the window is given, which is in the form of circular 6 centimeters. Transmissibility of glass tau equal 0.08. So according to the formula, the radiation of heat loss from the glass window is given by the equations. Q is equal to sigma B A to the power of 4 into tau. Here 2 is called transmissibility, which can be defined as the ratio of amount of heat transmitted to the total radiation of the heat now. So, according to these equations now, sigma B is given, which is equal to Boltzmann constant 5.67 into 10 to the power of minus 8. A is representing the area of the circular window, which is equal to A is equal to pi by 4 d to the power of 2 now. By using this equation, pi by 4 is equal to 3.14, d square is equal to, here is given 6 centimeters is given, so which can be written as now 0.06 meters, hence 0.06 meters whole square. According to these relations, this is nothing but relationship be used in these equations now. Into T to the power of 4, that is the temperature. Temperature always expressed in degree of Kelvin only. According to the problem, it is given 2250 to the power of 4 and the transmissibility is equal to 0.08. After doing the calculations, we got this value is equal to 328.53 watts. This is the amount of heat energy is transmitted through the window. The second problem, a thin metal plate of 4 cm diameter is suspended in atmospheric air whose temperature is 290 degree Kelvin. The plate attains a temperature of 295 degree Kelvin when one of its face receives radiant energy from the heat source at the rate of 2 watts. If heat transfer coefficient of both the surfaces of the plate is stated to be 87.5 watts per meter square per degree Kelvin, work out the reflectivity of the plates. So first to identify what is the given data in the problems. The metal plate diameter is given 4 centimeters. Atmospheric air whose temperature is, that is the treated as air initial temperature, which is equal to 290 degree Kelvin. The final temperature, that is after heating the plates, it attains 295. We are calling it is equal to T2. That is E is equal to, that is given the radiant energy that receives is equal to 2 watts. Heat transfer coefficient is given 87.5 watts per meter square per degree Kelvin. The heat loss by the conventions from both sides of the plate is given as both sides. Here 2 is nothing but representing the number of sides. Here 2 we are taken H into A into delta T now. Where H representing the heat transfer coefficient by using convection process. So A is equal to that area. Delta T is representing the difference of temperatures, that is the T2 minus the T1. So on substituting the values 2 into H is equal to 87.5 into area pi by 4 into 0.04 whole square into difference of temperature is equal to 295 minus 290, and doing the calculations we got this value is equal to 1.1 watts. But for the most of the solids, the transmittivity is 0. The energy lost by the reflection is equal to 2.0 minus 1.1, it is equal to 0.9. Here, according to the equations, we are having alpha plus gamma plus 2, it should be equal to 1 now. Where alpha is nothing but representing the subsorptivity of the given object. Rho is representing the transmitted, and tau is representing, that is the transmissivity, rho is representing reflectivity. But according to the problems here now, for the solids, when we are taking the transmissivity is equal to 0, hence heat loss by the reflection is equal to total heat is equal to 2.0, but 1.1 is nothing but heat already it is transmitted. The remaining is equal to 2.0 minus 1.1 is equal to 0.9 W. So reflectivity is equal to, it is the ratio of the total amount of energy that is reflected to the total energy that is incident, which is equal to 0.9 divided by 2.0, which is equal to 0.45. The third problem, a black body of total area 0.05 meter square is completely enclosed in a space bounded by 5 centimeter thick wall. The walls have a surface area of 0.5 meter square and thermal conductivity 1.07 watts per meter per degree Kelvin. If the inner surface of the envelope wall is to be maintained at 250 degree Kelvin, 215 degree Celsius, and outer wall surface is at 30 degree centigrade. Calculate the temperature of the black body. Neglect the difference between inner and outer surface areas of envelope materials. The total area is given now 0.05 meter square. This is nothing but given data. Wall thickness is given 0.05. Here is given in centimeters, which can be expressed here now. 0.05 divided by here 100 equal to 0.0005 meters. The inner surface temperature is given Ti, it is equal to 250 degree centigrade. Outer wall temperature is given, which since it is exposed to air, ambient temperature which is equal to 30 degree centigrade. The net heat radiated by the black body due to the enclosing wall is given by, here heat radiation is equal to sigma B into A into temperature difference, that is delta T to the power of 4 is required. That means TB to the power of 4 minus TW to the power of 4 now. So by using this relationship we got Q is equal to 5.67 into 10 to the power of minus 8. This is representing the sigma B value, and area is equal to 0.05 meters square is given, and TB to the power of 4 minus is given 480 to the power of 4. Here this values TB is the temperature of the black body in degree Kelvin we have to determine. So heat conducted through the wall is given by QC is equal to K into A into delta T divided by delta, where K is representing the thermal conductivity of the materials, A is in area of the cross section, delta T is representing the temperature differences, and here delta is representing the thickness of the glass, which is equal to 0.05 centimeters is given. And substituting the values, we got 1.07 into 0.5 into, that is the temperature difference is equal to 215 minus 30, which is given here now. On doing the calculations, we got this values is equal to 1979.5 watts. Under steady state conditions, the heat conducted through the wall must be equal to the radiation loss from the black body. Thus means which is equal to 5.67 into 10 to the power of minus 8 into 0.05 into T to the power of B to the power of 4 minus 482.4, which is already we have taken, it is equal to 1979.5 now. Because steady state conditions means the amount of heat energy that is transmitted here, it is equal to the amount of heat loss due to the radiations. Hence, by equating these two equations, we got TB to the power of 4 is equal to, we got 1979.5 divided by 5.67 into 10 to the power of minus 8 into 0.05 plus 488.88 to the power of 4. Doing the calculation we got, which is equal to 8349.47 into 10 to the power of 8. So TB equal to, which is equal to, that means it is a fourth root of 8349.47 into 10 to the power of 8, which is equal to, we got to 955.9 degree Kelvin. Okay, this is the required answer. Here another one, problem number 4. A polished metal pipe of 5 cm outside diameter and 370 degree Kelvin temperature at outer surface exposed to ambient conditions at 295 K temperature. The emissivity of the surface is given 0.2 and the convection coefficient of heat transfer is equal to 11.35 watts per meter square per degree Kelvin. Calculate the heat transfer by radiations and natural convections per meter length of the pipe. Take thermal radiation constant. What will be the overall coefficient of heat transfer by the combined mode of convections and radiations? Here the given that in the problem is metal pipe 5 cm diameter is given. That means the pipe diameter is equal to 5 centimeters. The temperature at the outer surface, it is given represented as T1, which is equal to 370 Kelvin. Ambient temperature, which is equal to 295 degree Kelvin. The emissivity of the surface is equal to 0.2. Convection coefficient of heat transfer, generally it is represented as H, which is equal to 11.35 watts per meter square per degree Kelvin. The surface area of the pipe is equal to Here is the given surface area. That is the perimeter multiplied by the length of the pipe, which is equal to pi into 0.05. Here 1 is representing the length of the pipe, which is equal to 0.157 meter square now. Radiation is equal to, according to the relations now, which is equal to this epsilon multiplied by sigma b into A into T1 to the power of 4 minus T2 to the power of 4 now. Here, from the given data, we got the emissivity of the surface is given by 0.2, which is represented here now, that is epsilon, into sigma b, which is known as Boltzmann constant, which is equal to 5.67 into 10 to the power of minus 8 is given. A is representing surface area, which is equal to 0.17157 meter square given. Here T1 to the power of 4, which is equal to 370 to the power of 4 minus T2 to the power of 4, which is equal to 295 to the power of 4. So on doing the calculations, we got to radiation is equal to 19.88 watts. Now QC is representing the heat transfer through conventions, which is given by the relations H into A into delta T, where H is representing the conventions heat transfer coefficient, which is given 11.35. A is equal to the surface area, which is given 0.157. Delta T is representing the difference of temperatures, which is equal to 370 minus 295. So according to these calculations, we got it is equal to 133.64 watts. So the total exchange, the total here energy is equal to 19.88 plus 133.64, which is equal to 153.52 watts. But the total heat exchange can be expressed as Q is equal to UA delta T, where U is representing the overall heat transfer coefficient, A is representing the area, that is area of the sections. Here we are taking it is equal to lateral surface. Delta T is representing the temperature difference. So from these relations, the overall coefficient is equal to U is equal to, we can take it as QT divided by A into delta T now. Here QT is equal to total energy, that is the transmitting, which is already we measured, which is equal to 153.52 divided by area of the cross section is equal to 0.157. Here we have taken this is nothing but lateral surface of the object. Delta T is equal to the different difference, which is equal to 370 minus 295 is given. So on doing the calculation, we got 13.04 watts per meter square per degree Kelvin. This is known as the overall heat transfer coefficient. Here problem number 5. Here two parallel rectangular surfaces, 1 meter by 2 meter, are opposite to each other at a distance of 4 meters. The surfaces are black and at 100 degrees centigrades and 200 degrees centigrades respectively. Calculate the heat exchange by radiation between two surfaces. Here two rectangular plates are given having the dimensions of 1 mm by 2 mm. Hence, the area is given by 1 by 2, it is equal to 2 meter square now. The distance, these two plates are separated by a distance of 4 meters. That nothing but according to the problems, which is equal to, here now, L is equal to 4 meters. So the surfaces are black at one is 100 degrees centigrade, one more is 200 degrees centigrade respectively. So here now, the heat transfer that taking place by the radiation process is equal to Q12, that nothing but the amount of heat energy that is transmitting from one surface to second surface. It is equal to A1 F12 sigma T1 to the power of 4 minus T2 to the power of 4 now. Here, since here the radiation process is taking place now, emissivity is equal to here now for the black body. Here observe it is 1, it is also equal to the emissivity. So we can write epsilon 1 is equal to epsilon 2, which is equal to 1 now. So B is equal to A by H now. Here, which is equal to 2 by 4, which is equal to 0.5 now. And C is equal to B by H, which is equal to 1 by 4, it is equal to 0.25 now. For the known values of B and C, you can find F12, that is here amount of, that is it is known as a C factor. From the graph, F12 is equal to 0.043 values. So Q12 is equal to the amount of heat transfer from 1 to T is given by A1, that nothing but equal to the area of the cross section, which is equal to 2 into 2 by 1. And F12 already we determined, which is equal to 0.043 values given, and sigma, which is equal to here now 5.67, and the difference is equal to here given now, that is 4.73 to the power of 4 minus 3.73 to the power of 4. Sorry, this one is nothing but 473 to the power of 4 minus here 373.4. So which is equal to now, and doing the calculation we got this value is equal to 149.7 watts now. Okay, this is the amount of heat energy transferred from surface 1 to 2 when they are maintaining at a temperature of 200 degrees centigrade and 100 degrees centigrade. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.